Welcome to this explainer. Today, we're diving into an absolute masterclass on the fundamental concepts of gravitation. We're going to explore everything from that legendary story of the falling apple right up to the heavy-hitting mathematics that actually govern planetary orbits. So if you've ever wanted a ground-up understanding of the invisible forces that are literally holding our universe together, you're in the right place. Let's jump right in. Here is our agenda for today. We'll be looking at gravity and centripetal force, the universal law, free fall and motion, mass versus weight, and finally, pressure, buoyancy, and Archimedes.
All right, starting off with Section 1, Gravity and Centripetal Force.
Okay, so picture Isaac Newton sitting under that famous tree. He suddenly realizes that the exact same force pulling down the apple is the one governing the moon. It's an awesome story, right? But it brings up a really fascinating question. Does the apple attract the Earth? Well, according to Newton's third law, for every action there's an equal and opposite reaction. Mathematically speaking, the apple actually does attract the Earth. It pulls with the exact same amount of force that the Earth uses to pull the apple. But here's the catch. Newton's second law tells us that acceleration depends on mass. And the Earth's mass is just so unbelievably massive compared to a tiny little apple that the Earth's acceleration towards it is completely undetectable.
Now, this perfectly illustrates how this force scales up. Think about a stone whirling around on a string. The tension in that string pulls the stone inward, constantly changing its direction and keeping it locked in a circle. We call this centripetal, or center-seeking force. Without that inward pull, the whirling stone, or for that matter, our moon, just wouldn't curve. It would fly straight off into space along a tangent line. The Earth's gravity is essentially acting as that invisible string for the moon. Moving right along to Section 2, the universal law.
So here is the golden rule. Every single object in the universe attracts every other object. That means, sir, the Earth attracts the moon, but it also means you are gravitationally attracting the friend sitting next to you right now. No joke. The first piece of this puzzle is that the force is directly proportional to the product of their two masses, which we usually represent as a big M and a little m. Second, distance plays a huge role here, but not in a simple, linear kind of way. The force actually weakens dramatically as you move away because it follows an inverse square rule. To put that in perspective, if the distance d between two objects increases by a factor of 6, the gravitational force doesn't just get 6 times smaller, it becomes 6 squared, or 36 times smaller. It drops off fast.
So when we combine those two proportionalities, we get the complete relationship. The force of gravity relies on the product of the two masses, big M times little m, divided entirely by the square of the distance between them, or d squared.
And this is where it all perfectly comes together. To turn that proportionality into a concrete mathematical equation, we just add g, which is the universal gravitation constant. This gives us a simple, incredibly elegant formula. F equals g times m, all over d squared. Honestly, it's one of the most beautiful equations in all of physics because it literally applies to everything in the cosmos. Now, what's really, really fascinating about this is how Newton actually figured out that inverse square rule. He didn't just guess it. He derived it by basically hacking Johannes Kepler's third law of planetary motion. Newton knew from centripetal acceleration that force is proportional to velocity squared over radius. He also knew Kepler had already proved that a planet's radius cubed over its time period squared is constant. So by substituting Kepler's constant into his own velocity equation, Newton mathematically proved that force absolutely must drop off by the square of the distance. Absolute genius, right? All right, let's look at Section 3, free fall and motion. Let's bring this cosmic math back down to Earth for a second. We can actually take our universal formula and adapt it just for our planet. If we swap out the big M for the mass of the Earth and the distance d for the radius of the Earth, we derive g, which is the acceleration due to gravity. Crunch those numbers and you get roughly 9.8 meters per second squared. But notice what's missing from this equation. Little m. The mass of the falling object isn't even in the formula. That means, in a vacuum, a giant heavy boulder and a tiny light pebble will fall at the exact same rate of acceleration. So, the real takeaway here is that for falling objects, like, a car humorously falling off a cliff in a classic textbook physics problem, we just take our standard equations of uniformly accelerated motion and swap the standard acceleration a with our newly found constant g. Suddenly, figuring out exactly how fast something is going to hit the ground becomes incredibly straightforward. Next up, Section 4, mass versus weight. Okay, we need a quick conceptual palate cleanser here to distinguish between two highly confused terms, mass and weight. We're all guilty of using these interchangeably in everyday life, but in physics, mixing them up is pretty much a cardinal sin. So let's clear it up. Your mass is an inherent, totally unchangeable measure of your physical inertia. It is literally how much stuff you're made of, measured in kilograms. If you blast off into deep space, your mass stays exactly the same. Your weight, on the other hand, is a force, measured in newtons. It's the result of gravity pulling on your mass, which means your weight completely changes depending on what planet you happen to be standing on. To see this location-dependent weight thing in action, let's just compare the actual celestial data for the Earth and the Moon. Notice how the Earth is significantly more massive and has a much larger radius than the Moon. Because the Moon has significantly less mass and a smaller radius, when we plug those specific numbers back into our universal gravitation formula, the calculation shows a massive drop in force. You would weigh exactly 1/6 on the Moon of what you weigh right now on Earth. Honestly, it's the ultimate quick weight loss program, though your mass and, sadly, how your clothes fit would remain entirely unchanged. Finally, we have Section 5, Pressure, Buoyancy, and Archimedes. Let's expand our concept of gravitational force down to physical surfaces and fluids. We're going to start with thrust, which is simply a net force directed perpendicularly at a surface. When we take that thrust and divide it by the area it's applied to, we get pressure. And this simple ratio is practically magic. It's precisely why a sharp knife cuts so easily, because all your pushing force is concentrated into this microscopically thin area, creating massive pressure. It's also exactly why a heavy camel can walk on loose desert sand without sinking. Their wide feet spread their weight over a much larger area, vastly reducing the pressure on the sand. And this leads us to how fluids push back. When you push an empty, sealed plastic bottle underwater and let it go, it violently bounces right back to the surface. Why? Because you're experiencing buoyancy. Gravity is absolutely pulling the bottle down, but the water is exerting an upward push, an upthrust on the object. Understanding this upward push brings us to Archimedes. You know, the ancient Greek scholar who famously shouted "Eureka" in his bathtub when he noticed the water level rising as he got in. The guy boasted a totally wild resume, designing levers, pulleys, and even war machines for the Greek army. But his absolute most enduring legacy is formulating the fundamental principle of buoyancy. Archimedes' principle states that the upward buoyant force exerted on a body immersed in a fluid is exactly equal to the weight of the fluid that the body displaces, and this elegantly explains a pretty great paradox. Why does a massive, incredibly heavy iron ship easily float on the ocean, while a tiny, lightweight iron nail just sinks straight to the bottom? Well, it's all about shape. The ship is shaped like a bowl, displacing a massive volume of water, which generates a massive upward buoyant force. The nail? It displaces almost no water, so gravity easily wins that fight. Now, to make the math easier across different materials, we use something called relative density. This is simply the ratio of a substance's density compared cleanly to the density of water. And because it's a ratio, it has no units. This precise understanding of density is exactly how Archimedes ultimately tested the purity of the king's gold crown, without having to melt it down to check the inside. He just compared its displaced water to that of pure gold. Brilliant. And that wraps up our explainer on the masterclass of gravitation. From the cosmic dance of the moon pulling the tides, all the way to the buoyant force pushing up a floating ship, we've seen how just a few elegant equations totally govern our reality. If these invisible forces define the entire universe so beautifully, it really makes you wonder, what other hidden physical laws are quietly dictating your everyday life, right under your nose? Keep wondering, keep learning, and we'll catch you in the next explainer.